Hi. In this problem, we're going to be dealing with a variation of the usual coin flipping problem. But in this case, the bias itself of the coin is going to be random. So you can think of it as you don't even know what the probability of heads for the coin is. So as usual, we're still taking one coin and we're flipping it n times. But the difference here is that the bias is as a random variable q. And we're told that the expectation of this bias is some mu, and that the variance of the bias is some sigma squared, which we're told is positive. And what we're going to be asked is to find a bunch of different expectations, covariances, and variances. And we'll see that this problem gives us some good exercise in a few concepts. Law of iterated expectations, which, as again, tells you that when you take the expectation of a conditional expectation, is just the expectation of the inner random variable. The covariance of two random variables is just the expectation of the product minus the product of the expectations. The law of total variance is the expectation of a variance, of a conditional variance, plus the variance of a conditional expectation. And the last thing, of course, we're dealing with a bunch of Bernoulli random variables, coin flips. So as a reminder, for a Bernoulli random variable, if you know what the bias is some known quantity p, then the expectation of a Bernoulli is just p, and the variance of the Bernoulli is p times 1 minus p. Okay, so let's get started. The problem tells us that we're going to define some random variables. So xi is going to be a Bernoulli random variable for the ith coin flip. And so xi is going to be 1 if the ith coin flip was heads, and 0 if it was tails. And one very important thing that the problem states is that conditional on q, the random bias, if we know what the random bias is, then all the coin flips are independent. And that's going to be important for us when we calculate all these different values. Okay, so the first thing that we need to calculate is the expectation of each of these individual Bernoulli random variables, xi. So how do we go about calculating what this is? Well, the problem gives us a hint. It tells us to try using the law of iterated expectations. But in order to use it, you need to figure out what you need to condition on. Right? What is this y? What takes the place of y? And in this case, a good candidate for what you condition on would be the bias, the q that we're unsure about. And so let's try doing that and see what we get. So we write out the law of iterated expectations with q. So now, hopefully, we can simplify what this inner conditional expectation is. Well, what is it really? It's saying, given what q is, what is the expectation of this Bernoulli random variable xi? Well, we know that if we knew what the bias was, then the expectation is just the bias itself. But in this case, the bias is random. But remember, a conditional expectation is still a random variable. And so in this case, this actually just simplifies into q. Right? So whatever the bias is, the expectation is just equal to the bias. Right? And so that's what it tells us. And this part is easy because we're given that the expectation of q is mu. All right. And then the problem also defines a random variable x. X is the total number of heads within the n tosses, or you can think of it as a sum of all these individual xi Bernoulli random variables. And now, what can we do with this? Well, we can remember that linearity of expectations allows us to split up this sum. An expectation of a sum, we can split up into a sum of expectations. So this is actually just expectation of x1 plus dot 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 plus all the way to expectation of xn. All right. And now, remember that we're flipping the same coin. We don't know what the bias is, but for all the n flips, it's the same coin. And so each of these expectations of xi should be the same no matter what I is. Right? And each one of them is mu. We already calculated that earlier. And there's n of them, so the answer would be n times mu. So let's move on to part B. Part B now asks us to find what the covariance is between xi and xj. And we have to be a little bit careful here because if there are two different scenarios, one where I and j are different indices, different tosses, and another where I and j are the same. So we have to consider both of these cases separately. Let's first do the case where x and I are different. So I does not equal j. In this case, we can just apply the formula that we talked about in the beginning. So this covariance is just equal to the expectation of xi times xj minus the expectation of xi times expectation of xj. All right. So we actually know what these two are, right? Expectation of xi is mu. Expectation of xj is also mu. So this part is just mu squared. But we need to figure out what this expectation of xi times xj is. Well, the expectation of xi times xj, we can again use the law of iterated expectations. So let's try conditioning on q again. And remember, we said that this second part is just mu squared. All right. Well, how can we simplify this inner conditional expectation? Well, we can use the fact that the problem tells us that conditioned on q, the tosses are independent. So that means that conditioned on q, xi and xj are independent. And remember, when random variables are independent, the expectation of a product, you can simplify that to be the product of the expectations. And because we're in the conditional world on q, you have to remember that it's going to be a product of two conditional expectations. So this will be expectation of xi given q times expectation of xj given q minus the mu squared still. All right. Now, what is this? Well, the expectation of xi given q, we already argued earlier here that that should just be q, right? And then the same thing for xj, that should also be q. So this is just expectation of q squared minus mu squared. All right. Now, if we look at this, what is the expectation of q squared minus mu squared? Well, remember, mu is just, we're told that mu is the expectation of q. So what we have is the expectation of q squared minus the quantity expectation of q squared. And what is that exactly? That is just the formula or the definition of what the variance of q should be. So this is, in fact, exactly equal to the variance of q, which we're told is sigma squared. All right, so what we found is that for I not equal to j, the covariance of xi and xj is exactly equal to sigma squared. And remember, we're told that sigma squared is positive. So what does that tell us? That tells us that xi and xj, for I not equal to j, these two random variables are correlated. And so because they're correlated, they can't be independent. Remember, if two random variables are independent, that means they're uncorrelated. But the converse isn't true. So, but if we do know that two random variables are correlated, that means that they can't be independent. Right? All right, and now let's finish this by considering the second case. The second case is when I actually does equal j. And in that case, well, the covariance of xi and xi is just another way of writing the variance of xi. Right? So covariance of xi It's just the variance of xi. And what is that? That is just the expectation of xi squared minus expectation of xi quantity squared. All right. And again, we know what the second term is. The second term is expectation of xi quantity squared. Expectation of xi, we know from part A, is just mu. Right? So that's just second term is just mu squared. But what is the expectation of xi squared? Well, we can think about this a little bit more, and you can realize that xi squared is actually exactly the same thing as just xi. And this is just a special case because xi is a Bernoulli random variable. Because Bernoulli is either 0 or 1. And if it's 0 and you square it, it's still 0. And if it's 1 and you square it, it's still 1. So there's squaring it doesn't actually change anything. It's exactly the same thing as the original random variable. And so because this is a Bernoulli random variable, this is exactly just the expectation of xi. And we said this part is just mu squared. So this is just expectation of xi, which we said was mu. So the answer is just mu minus mu squared. Okay, so this completes part B. And the answer that we wanted was that, in fact, xi and xj are not independent. All right, so let's write down some facts that we'll want to remember. One of them is that expectation of xi is mu. And we also want to remember that what this covariance is. The covariance of xi and xj is equal to sigma squared when I does not equal j. So we'll be using these facts again later. And the variance of xi is equal to mu minus mu squared. All right. So now let's move on to the last part, part C, which asks us to calculate the variance of x in two different ways. So the first way we'll do it is using the law of total variance. So the law of total variance will tell us that we can write the variance of x as a sum of two different parts. So the first is variance of x, expectation of the variance of x conditioned on something, plus the variance of the conditional expectation of x conditioned on something. And as you might have guessed, what we're going to condition on is q. Okay. Let's calculate what these two things are. So let's do the two terms separately. What is the expectation of the conditional variance of x given q? Well, what is this? We can write out x, because x, remember, is just a sum of a bunch of these Bernoulli random variables. And now, what we'll do is we'll again use the important fact that the x's we're told are conditionally independent, conditioned on q. And because they're independent, remember the variance of a sum is not the sum of the variance. It's only the sum of the variance if the terms in the sum are independent. And in this case, they are conditionally independent given q. So we can, in fact, split this up and write it as the variance of x1 given q plus all the way to the variance of xn given q. Okay. And in fact, all these are the same, right? So we just have n copies of the variance of, say, x1 given q. Now, what is the variance of x1 given q? Well, x1 is just a Bernoulli random variable, but the difference is that for x, we don't know what the bias or what the p is, right? Because it's some random bias q. But just like we said earlier in part A, when we talked about the expectation of x1 given q, this is actually just q times 1 minus q. Because if you knew what the bias were, it would be p times 1 minus p. So the bias times 1 minus the bias. But you don't know what it is. But if you did, it would just be q. So what we do is we just plug in q, and you get q times 1 minus q. All right. And now this is expectation of n. You can pull out the n. So it's n times the expectation of q minus q squared, which is just n times expectation of q. We can use linearity of expectations again. Expectation of q is mu. And expectation of q squared is, well, we can do that on the side. Expectation of q squared is the variance of q plus expectation of q quantity squared. Right? So that's just sigma squared plus mu squared. And so this is just going to be then minus sigma squared minus mu squared. All right, so that's the first term. Now let's do the second term. The variance of the conditional expectation of x given q. And again, what we can do is we can write x as the sum of all these xi's. And this, now we can apply linearity of expectations. So we would get n times one of these expectations. And remember we said earlier, the expectation of x1 given q is just q. So it's the variance of n times q. And remember now, n is just it's not random, it's just some number. So you can, when you pull it out of a variance, you square it. So this is n squared times the variance of q. And the variance of q we're given is sigma squared. So this is n squared times sigma squared. All right, so the final answer is just a combination of these two terms. This one and this one. So let's write it out. The variance of x then is equal to, we can combine terms a little bit. So the first one, let's take the mu's and we'll put them together. So it's n mu minus mu squared. And then we have n squared times sigma squared from this term, and a minus n times sigma squared from this term. So it would be n squared minus n times sigma squared, or n times n minus 1 times sigma squared. So that is the final answer that we get for the variance of x. And now, let's try doing it another way. So that's one way of doing it. That's using the law of total expectations and conditioning on q. Another way of finding the variance of x is to use the formula involving covariances, right? Because, and we can use that because x is actually a sum of multiple Rayner variables x1 through xn. Okay, and the formula for this is you have n variance terms plus all these other ones where I is not equal to j, you have the covariance terms. And really, it's just, you can think of it as a double sum of all pairs of xi and xj, where if I and j happen just to be the same, then it simplifies to be just the variance. No, so we pulled these n terms out because they are different than these, because they have a different value. All right, and now fortunately we've already calculated what these values are in part B, so we can just plug them in. All the variances are the same, and there's n of them, so we get n times the variance of each one. The variance of each one we calculated already was mu times mu minus mu squared. And then we have all the terms where I is not equal to j. Well, there are actually n squared minus n of them. So because you can take any one of the n to be the first to be I, any one of the n to be j. But then you have to, so that gives you n squared pairs. But then you have to subtract out all the ones where I and j are the same, and there are n of them. So that leaves you with n squared minus n of these pairs where I is not equal to j. And the covariance for this case where I is not equal to j, we also calculated in part B. That's just sigma squared. All right, and now if we compare these two, we'll see that they are fortunately exactly the same. So we've used two different methods to calculate the variance. One using this summation, and one using the law of total variance. So what do we learn from this problem? Well, we saw that first of all, in order to find some expectations, it's very useful to use law of iterated expectations. But the trick is to figure out what you should condition on, and that's some kind of an art that you learn through more practice. But one good rule of thumb is when you have kind of a hierarchy or layers of randomness, where one layer of randomness depends on the randomness on the layer above. So in this case, whether or not you get heads or tails depends on, that's random, but that depends on the randomness on the level above, which was the random bias of the coin itself. So the rule of thumb is when you want to calculate the expectations for the layer where you're talking about heads or tails, it's useful to condition on the layer above, where that is, in this case, the random bias. Because once you condition on the layer above, that makes the next level much simpler, because you kind of assume that you know what all the previous levels of randomness are, and that helps you calculate what the expectation for this current level is. And the rest of the problem was just kind of going through exercises of actually applying these tools. All right, so I hope that was helpful, and see you next time.